We're going to talk about calculating work. So as I said last time, work is equal to the force dotted into the displacement vector, force times distance, which is equal to force times the distance, magnitude, times the cosine of the angle between the force and the motion. So let's see, consider we have a mass M, and it's sitting on a table, and we apply a force F at an angle of theta to the plus x direction. Now we know that in order, we have the weight mg down, we have the normal force up, and we know that in order for it not to fly off the table, we have to have an equation balance that the summation of the forces in the y direction, let's write that, is equal to the mass times the acceleration in the y direction, but we want that to be 0, because it's initially at rest, and the acceleration is 0. So let's write this equation. The summation of the forces in the y direction, it's equal to the normal force minus mg plus f sine theta. This has to be equal to 0. So let's let the force be equal to 10 newtons. Let's let theta be equal to 60 degrees. What does that tell us? Well, it does tell us the normal force. The normal force is equal to mg minus f sine theta. Let m also be defined. Let m equal 1 kilogram. G is 9.8. So this is 1 kilogram times 9.8 meters per second squared minus 10 newtons times the sine of 60 degrees so this is 9.8 newtons minus 5 newtons, which is equal to 4.8 newtons. The reason why it's 5 is sine of 60 degrees is 0.5. So we get a minus 5 newtons. And it's the normal force, magnitude. Don't get it confused with the sine newtons. But the normal force, and it's 4.8 newtons. Well, that's a start. Continuing along, we need to do the equation of motion in the x direction. F's summation of the forces in the x direction is equal to the mass times the acceleration in the x direction. AX. We know it's AX. So what does this mean? What forces do we have in the x direction? We only have one. We have F cosine theta is equal to m times the acceleration in x direction. Well, let's suppose that the acceleration is 1 meter per second squared. So AX is equal to 1 meter per second squared. And m is 1 kilogram. Well, we can do it that way, but we already defined what the force was. I was going to say compute the force for a 1 meter per second squared. We don't need to do that. We already know that the force is 10 newtons. So what's the acceleration in x direction? It's equal to 10 newtons times the cosine of 60 degrees divided by 1 kilogram. So acceleration in the x direction is equal to cosine of 60 is 0.5. So this is 5 newtons divided by 1 kilogram, which is equal to 5 meters per second squared. So the acceleration in the x direction, as we apply this force of 10 newtons at an angle of theta equals 60 degrees, is 5 meters per second squared. Well, let's get another piece of paper and go to the next part. So we already found out that the acceleration in the x direction is equal to 5 meters per second squared. I'm going to ask the question, assume that V0x is equal to 0. It starts from rest. There's no friction because we already drew these are the only forces, the normal force, the weight down mg, and the applied force F. There's no other forces on the mass m. So we can see that how far does it go? What is its velocity? Or how long, let me change it this way. How long does it take for the final velocity to be 1 meter per second? How long does it take? Well, we know V final is equal to V initial. I'll put x here, just plus the acceleration times the time. Well, ax is 5. V0x is 0. So we can see that if t is equal to 0.2 seconds, that implies that the final velocity, v final of x, is equal to 1 meter per second. Okay, well that's cool. In 0.2 seconds, how far does it travel? X is equal to x naught plus v naught t plus 1/2 at squared. Let x naught be 0. V naught we know is 0. Therefore, in 0.2 seconds, it travels 1/2 times 5 meters per second squared times 0.2 squared. Well, this is equal to 5 times... You can do it several ways, but 5 times 0.2 is 10 times a minus 1 to the 10 to the minus 1, which is 1. So it's 0.2 divided by 2, which is equal to 0.1. You can kind of see that. 0.1 meters. Let's just check it again. 2 divided by, just write it out, 1/2 times 5 times 0.04. 5 times 0.04 is 0.2, and 0.2 divided by 2 is 0.1. So you can kind of do that in your head without a calculator. So in 0.2 seconds, the block travels 0.1 meters. So you can kind of do that in your head without a calculator. So in 0.2 seconds, the block travels 0.1 meters. So how much work is done by this force? Well, so let's put D is equal to 0.1 meters. If it travels 0.1 meters, how much work is done? Work is equal to the force vector, force, times the distance, times the cosine of this angle. The angle between the applied force and the direction of the motion. The direction of the motion is in the plus x direction. So it's cosine 60 degrees. The force, we said, is 10 newtons. The distance is 0.1 meters. And the cosine of 60 degrees is 0.5. So this is 10 times 0.1, which is 1 times 0.5, or 0.5 Newton meters, newtons times meter, which is a joule. So that's the amount of work that's done. And how fast is it going when it gets to that point, when we receive that much work? It's a good question. We already said it was going. We didn't say. Yes, we did. It's going 1 meter per second after 0.2 seconds. Well, let's check this out. The initial energy had zero velocity, so it's kinetic. Initial energy is kinetic energy initial plus potential energy initial. You'll learn about this later if you didn't see it yet, but kinetic energy, a lot of times people write it potential energy, 0, the initial. Kinetic energy is equal to 1/2 mv, since it's initial, squared, plus potential energy. We're going to call it 0 because its height is 0. You'll learn about that soon enough if you didn't get to it yet. So the initial energy is 1/2 mv naught squared, but v naught is 0. So the initial energy is 0. What about the final energy? The final energy is equal to the kinetic energy at the final state plus the potential energy in the final state, which is 0. So kinetic energy final is 1/2 mv final squared. Therefore, the final the final energy is going to be equal to the initial energy, which is 0, plus the work. So the final energy is equal to the initial energy plus the work that was done on it. So the final energy is just equal to the work. So 1/2 mv final squared is equal to 0.5 joule. Rewriting this, I want to keep it on the paper. Let me kind of just write it up here a little bit. Let's just rework this. So V final squared is equal to 2 times 0.5, which is 1, divided by the mass. So it's 1 joule. 2 times 0.5 is 1, divided by the mass, and we said the mass is 1 kilogram. So V final is the square root of 1. Joule is a Newton meter. Has to have units of meters per second. The velocity is 1 meter per second. V final. Well, that's what we computed up here. So I just showed you how to use energy conservation and the concept of work to get the final velocity of this object, of this mass m, as it was pulled with a force of 10 newtons at an angle of 60 degrees for amount of time of 0.2 seconds. 0.2 seconds. It traveled a distance of 0.1 meters. And its work, the work done by that force was 0.5 joule. Now I'm introducing the concept of energy equal to kinetic energy plus potential energy. The initial energy is equal to the final energy. That's called energy conservation. There are no dissipated forces in this case, no friction. Therefore, the initial energy is equal to the final energy. But the final energy was increased by the amount of work that was done. The work is equal to 1/2 0.5 joule. Equating the equation, you get V final is equal to 1/2 mv, 1/2 V final is equal to 1 meter per second, which is exactly what we had up here. So there's a walkthrough.